Radical reactions occur whether heterolytic cleavage or homolytic cleavage. Okay, for heterolytic cleavage, up to this point, you used to see reaction where the electron move together. For example, if I have a bond between A and B, I don't want to show the bonds breaking, you used to draw an arrow from the bonds to the atom that is collapsed onto, followed by the Yates arrow and the result. Since both of electron collapse onto B, A is left with nothing and B left with both electrons together. This is called heterolytic cleavage, where hetero tells us that the difference, lytic is to collide and cleavage is to break. The hetero tells us that the two atoms do not get the same number of electrons. A got nothing and B got two. The mechanism arrow of the heterolytic cleavage has that double hook where I like to think is one dot of each of this hook to represent the two electrons are moved together. What is radical? A radical is reactive intermediate with a single ampere electron having a very short lifetime. Radical reactions are not ionic reactions judged by the frontier molecule orbital approach and not the nucleophilicity or electrophilicity concept. Carbon radicals are classified as 1, 2, or 3 degrees. This is generated by the homolysis of a covalent bond. Radical is represented by an atom with one dot. Electronic movement involving radicals are represented using half-headed fishhook arrows. In a radical reaction, we have homolytic cleavage where homo means the same, lytic is to lyse, and the cleavage tells us the type of reactions we're doing. To show a homolytic cleavage, you start your arrow at the electron that is going to move, and you draw a single-headed or a fishhook arrow where you can imagine that one point is just a single electron and another arrow from the another electron is the another atoms against one electron at the time. Homo means the same tell us that each of these atoms get the same number of electrons when the bond is broken, which means that A has a single ampere electron or a radical and B has a single ampere radical electron. Both of these are going to be very reactive. A carbon radical is sp hybridized with an unpaired single electron occupying an unhybridized p orbital having trigonopyramidal or planar geometry possessing an angle of 120 degrees. In the most cases, the pyramidal geometry is observed, especially when the heteroatoms are pi-electron donating substituents of electronegative groups like fluorine or oxygen are present. However, some of the lower group of alkene class like methyl possess planar geometry, and T-butyl show the pyramidal geometry with a slight characteristic or of planar geometry. The energy required to invert the geometry is very low in the case of the flexibility pyramidal geometry. Radicals are formed from the covalent bond by adding energy in the form of heat or light. Some radical reactions are carried out in the presence of a radical indicator, a compound that contains an especially weak bond that serves as a source of a radical. Parasites, compound with the general structure ROOR, that the most commonly used a radical indicator. Hitting a parasite readily caused by homolysis of the weak oxygen bond, forming a 2RO radical. For two common reactions of radical, we have two types of reaction, which is first, reaction of radical with a CH bond radical. Okay, from the reaction above, it abstracts a hydrogen atom from the CH are bound to form a SH and a carbon radical. One electron from the CH bond is used to form a new HX bond, and another electron in the CH bond remains on the carbon. The result is that original radical X is now surrounded by the octet of electrons and the new radical is formed. This radical reaction is typically seen with a nonpolar CH bond of alkenes, which cannot react with a polar or ionic electrophiles and neutrophiles. For the second type of reaction, which is reaction of radicals with carbon-carbon double bond. From the equation below, a radical X also adds to the pi bond of the carbon-carbon double bond. One electron from the double bond is used to form a new CX bond, and another electron remain on the other carbon originally part of the double bond. For two radicals react with each other, a radical once forms rapidly react with whatever is available. Usually that means a stable of sigma or pi bonds. Occasionally, however, two radicals comes into the contact with each other and they react to form a sigma bonds. The reaction of a radical with oxygen, a diradical, and in its ground state electronic configuration is another example of two radicals react with each other. In this case, the reaction of oxygen with X from a new radical, thus preventing X from react with an organic substrate. Compounds that prevent a radical reaction from occurring are called a radical inhibitor or radical scavengers. The fact that these compounds inhibit a reaction often suggests that the reaction occurs via radical intermediates.
General reaction for halogenation of alkenes. In the reaction, an alkene CH would react with a halogen molecule X2 in the presence of UV light or heat to produce alkyl halide and halogen acid. X in a general reaction would represent a halogen, and as we know it, halogen elements are fluorine, chlorine, bromine, and iodine. However, fluorine is too reactive due to the low activation energy, to the point of fluorine becomes an explosive when reacted with an alkene. Meanwhile, iodine is not reactive due to the energy becomes endothermic in the propagation step. There is no reaction between iodine and alkane in normal lab conditions, as the energy needs to become exothermic in the propagation step. Mechanism of halogenation. Halogenation of alkane that undergoes radical substitution reaction have one type of mechanism only, regardless of the alkane and halogen use. This is a contrast from nucleophilic substitution that could either went through SN1 or SN2 mechanism depending on their starting material and the reagents used. How do we know that the halogenation of alkane is actually a reaction that involves radical intermediates instead of an ionic one? There are three reasons that would support this theory. The first reason is that UV light, heat, or added peroxide is necessary for the reaction. Light or heat would provide the energy needed for the reaction for homolytic bond cleavage to form radicals. In addition, breaking the weak oxygen bond of peroxide would initiate the radical reaction as well. The second reason is that oxygen could inhibit the reaction. The diradical oxygen could remove radical from reaction mixture, thus preventing reaction. If the reaction is not a radical one, the addition of oxygen wouldn't disrupt the reaction at all. The third reason would be that no rearrangement are observed because radicals do not rearrange. The steps of halogenation. In general, all reactions that would involve radical intermediate would follow these three general steps. The first step is the initiation, the second step is propagation, and the third step is termination. Let's go to the reaction one by one. In this example use, we would use ethane as the alkane with chlorine molecule as the halogen. In the presence of UV light or heat, this would produce chloroethane with hydrochloric acid. The first step, initiation. This is where homolysis happens to form two radicals. The cleavage of the weakest bond in the starting materials, in this case is the chlorine-chlorine bond, would require energy from UV light or heat. The movement of the electron in the bond is shown by the fishhook arrow, where one electron each goes to one chlorine atom. The chlorine atom would now have one anti-electron making it a chlorine radical. Step 2. Propagation. This is where one radical reacts and a new radical is formed. The chlorine radicals from initiation step will abstract a hydrogen atom from ethane as shown in step 2. This would form the HCl bond and leave one unpaired electron on carbon, generating the ET radical. After that, the ET radical will abstract a chlorine atom from a new chlorine radical as shown in step 3. This would form the chloroethane and a new chlorine radical. As step 2 and step 3 both would produce a radical, these radicals would continue to react with a new ethane and chlorine molecule, producing more and more radicals. Hence, step 2 and step 3 will be repeated over and over again in a long chain mechanism. After a long chain of reaction, we would finally get to step 3, the termination step. This is where two radicals would react together to form stable sigma bonds, thus ending the reaction. There are three ways that the combination could happen, and we show it as 4A, 4B, and 4C. In 4A, the chlorine radicals would react together to form a new chlorine molecule. In 4B, the ethene radicals would react together to form butane, and in 4C, ethene radicals and chlorine radicals would react together to form chloroethane. In the reaction between ethane and chlorine, the product that we wanted is chloroethane. Hence, only the reaction in 4C is given focus on.
There are interestingly no equal reactivity for each of the hydrogens in a complex alkene. At 25 degrees Celsius, light-induced gas phase coordination gives 45% 1-chloropropane and 55% 2-chloropropane. Next, at 25 degrees Celsius, light-induced gas phase bromination gives 97% 2-bromopropane of the mono-bromo product. As a result, secondary hydrogens are inherently more reactive than primary hydrogen by a factor of 3:1 ratio. The last equation is light-induced coordination of 2-methylpropane gives 65% 2-chloro-2-methylpropane, the substitution of product of the sole tertiary hydrogen. Because the observed ratio is 1:1, the secondary CH bond must be reactive, which is easier to homothetically cleave than primary CH bond. As a result, the weaker the CH bond, the easier the hydrogen atom is removed in radical halogenation. When the alkene reacts with chlorine, a mixture of products is formed. Alright, we start with bromination. Bromine radicals can take one or two hydrogen atoms from hydrogen and one from propane. Using bond dissociation energy reveals that both reactions are endothermic, although the more stable two radicals need less energy to produce. To be concluded, because bromination rate determining process is endothermic, single radical halogenation products win because more stable radicals generate faster. Next, we go to the coordination. The transition state to create both radicals resemble the other thicker starting material, propane, since coordination has an exothermic rate determining step. As a result, the relative stability of the two radicals is significantly reduced, and both radicals are created. To be concluded, because coordination rate determining phase is exothermic, the transition state mimics the starting materials, both radicals are produced, and a mixture of product is formed. What is the meaning of Hammond postulate? Hammond postulate is the transition state of a reaction resembles either the reactants or the product to whichever it is closer in energy. In an exothermic reaction, the transition state is closer to the reactants than to the products in energy. In an endothermic reaction, the transition state is closer to the products than to the reactants in energy. You must want to know more about antioxidant, right? Let's find out. An antioxidant is a substance that inhibits the oxidation reaction. Antioxidants found in nature, such as vitamin E, protect cells from damaging radical reactions. To prevent oxidation and spoiling, synthetic antioxidants such as BHT are added to package and coolants. Vitamin E and BHT are radical inhibitors, which mean they react with radicals to break the chain of radicals. As a result, numerous anti-aging formulations, including antioxidants such as vitamin E, have become popular consumer items.
Radical addition reaction to rubber bonds. The second common reaction of radical is addition to double bonds. An alkene contains an electron-rich, easily broken pi bond. It reacts with an electron-deficient radical. Radicals react with alkenes via a radical rate chain mechanism that consists of initiation, propagation, and termination steps. Mechanism of the radical addition of HBr to an alkene. HBr addition to an alkene from radical intermediates proceeds by a mechanism with three distinct parts: initiation, propagation, and termination. So the first part is initiation. Steps 1 and 2 involves the abstraction of H from HBr occurs by a two-step process. The first process is ROOR to initiate the reaction. Two steps are needed to form Br. The second is homolysis of the OO bond of the peroxide forms RO, which abstract a hydrogen atom from HBr to form Br. The second part is propagation. Steps 3 and step 4 involve the pi bond is broken. The CH and CBr sigma bonds are formed. The first step of propagation forms the CBr bond when the Br radical add to the terminal carbon, leading to a second degree carbon radical. The second degree radical abstract a H atom from HBr, forming the new CH bond and completing the addition reaction. Because a new Br radical is also formed in these steps, step 3 and step 4 occur repeatedly. The last part is termination. Step 5 involves two radicals to react to form a bond. To terminate the change, the two radicals, for example, two Br radicals react with each other to form a stable bond, preventing further propagation via step 3 and step 4. With propane, there are two possible paths for this step, depending on which carbon atom of the double bond forms the new bond to bromine. The most stable 2-degree radical forms faster, so path B is preferred. So in both reactions, H and Br add to the double bond, but the order of the addition depends on the mechanism. Radical halogenation at an allylic carbon. Homolysis of the allylic CH bond of propane generates the allyl radical, which has an unpaired electron on the carbon adjacent to the double bond. The weaker the CH bond, the more stable the resulting radical. An allyl radical is more stable than a 3-degree radical. The allyl radical is more stable than other radicals because two resonance structures can be drawn from it. Application: oxidation of unsaturated lipids. Step 1. Oxygen in the air absorbs an allylic hydrogen atom to form an allylic radical because the allylic CH bond is weaker than the other CH bonds. The second step, the allylic radical reacts with another molecule of oxygen to form a peroxide radical. This last step, the peroxide radical extracts an allylic hydrogen from another lipid molecule to form a hydroperoxide and another allylic radical that continues the change. Step 2 and 3 can repeat again and again until some other radical terminate the chain.
Polymerization. Polymerization is the process of chemically combining the monomers to create a larger molecule. Compared to a small molecule, polymers are beneficial in the way that they generally have higher viscosities, higher boiling points, and can show improved mechanical strength over their monomers. In the example here, we have three monomers, ethylene, joined together in polymerization, becoming the polymer polyethylene. Polymers exist naturally as a part of our life, such as in proteins, in carbohydrates, and in cellulose. However, polymers can also be made synthetically and is a crucial part in industry for plastic products, such as polyethylene, polyvinyl chloride, PVC, and polystyrene. In the table here, we have some examples of the monomer, the polymer, and the products made from them. We have vinyl chloride that would produce polymer polyvinyl chloride PVC, and they are used to make PVC blood bags and tubings. Another example is the monopropene that would produce polypropylene and would make polypropylene syringes. The third example is tetrafluoroethylene, which makes the polymer polytetrafluoroethylene Teflon, and they are used to make dental floss. Radical polymerization. The general structure for polymer is CH2 bonded with CH-Z. The Z group will affect the physical properties of the polymer. Normally, Z is located on every other carbon atom on the polymer chain. Polymerization also operates through the three general steps of radical reaction, which is the initiation, propagation, and termination. A notable difference in polymerization would be the addition of carbon radical instead to an alkene instead of halogen or HBr. The carbon radical would be added to the bond of the alkene. The first step is initiation. This is where a carbon radical is formed by a two-step process. The chain initiation would begin with homolysis of the weak oxygen bond of the peroxide to form RO radicals. Then, it adds to a molecule of monomer to form a carbon radical. Step 2 is propagation. This is where the polymer chain grows. In step 3, the carbon radical formed during initiation adds to another alkene molecule to form new carbon-carbon bond and another carbon radical. The unpaired electron will always be located on the carbon atom having the Z substituent. The new carbon radical would react with a new alkane and continue the long polymer chain. Thus, step 3 would be repeated again and again. Finally, we would get to step 3, the termination step. And this is where two radicals combine to form a stable bond together. The carbon radicals on each chain would react together to form a bond, and this would create an even longer chain of polymer. When a carbon radical from a chain reacts with a new alkane, how do we know where would the new radical be formed? Hence, we would follow the head-to-tail polymerization, where the more substituted radical always adds to the less substituted end of the monomer. The new radical would always be located on the C bonded to the Z. And that is all about radical reaction, brought to you by Team 8. Thanks for watching. See you next time.